I'm Ennemcien. We have seen the basic force equation of a helical spring under deformation. That is, restoring force developed in a deformed spring is Fr equals minus Kx. That is the basic equation, where x represents the elongation or increase in length of the spring, or x is the compression, decrease in length of the spring. K is a constant of the spring called stiffness, spring factor, spring constant, force constant, or spring elasticity. Higher the value of K, stronger will be the spring. That is, it will be difficult to stretch out or compress the spring. Smaller value of K means the spring is light and it is easy to extend or compress. If you cut a spring into pieces, each piece has its own K depending upon its length. So spring factor of a part of a spring depends on the length of that part. Of course, if it is cut from the same spring, the relation is this: stiffness is inversely proportional to length. That is, K is proportional to 1 by L, or K into L is a constant. Longer a spring means it is easy to stretch or compress. A short piece of spring is difficult to compress, much more difficult to compress or extend. So K into L is a constant. That is the second relation connected with a helical spring. Of course, if you consider two pieces of length L1 and L2, then this equation, basic equation, takes the form K1L1 equals K2L2. Or you can generalize K1L1 equals K2L2 equals K3L3 equals etc. Now we pass to a fewer points, much more important. Say, see this figure. M is a block of mass M suspended from a vertical spring attached to a rigid support. Initially it extends the spring to a certain amount. We call it static extension, small e, and comes to a static state or equilibrium state. Now new length of the spring is L plus E. The applied force here, Fa, is the weight of the suspended block. That is, Fa equals mg. As the Hooke's law says, the restoring force inside the spring, that is numerically or equal in magnitude to the applied force. So Fa equals mg or Fr equals Fa, and Fr equals minus K into extension. Here extension is E, so Fr equals Fa equals minus Ke. If you neglect the negative sign, of course, if you require only the magnitude, then the equation becomes Fr, modulus of Fr, that is only magnitude we are considering, equals K into E. Fr is of course equal to Fa, which is equal to mg. That means mg equals K into E. From this equation, you can find out K, stiffness of that piece of spring. Now, if you pull the block down from its initial equilibrium position O to O dash by an amount x, a new restoring force will develop within the spring. This new restoring force, Fr, will be equal to minus K into x. Of course, this Fr is equal to the newly applied force for extension. If you use the Newton's second law, Fr equals ma, mass into acceleration. So you get the final answer as ma equals minus kx, or acceleration of the block, suspended block, A equals minus kx by m, or acceleration equals minus k by m into x. This is the differential equation of the spring load system. This equation is of very, very importance, as we will see later when we consider oscillations. Now, there is another extension, dynamical extension, which will come later. So, our points, concluding points, we have some important equations. One is the basic spring equation, that is Fr equals minus K into extension. Another one is K into L is a constant. Yet another, acceleration caused by a suspended load is A equals minus K by m into x. This last equation, we call it as differential equation of the spring load system. This equation is very, very important. Why we call this as differential equation will come later, because acceleration is expressed as a differential coefficient. We'll come to that point later. Then the next point is combinations of springs. You can connect 2 or 3 or 2 or more springs either in series or in parallel. So, here 3 springs with the stiffness values K1, K2, K3 are connected end to end as a chain. This is a series combination, just like resistance connection. Here, the equivalent K factor obeys reciprocal law. That is, the equivalent K of the combination, let it be K. 1 by K equals 1 by K1 plus 1 by K2 plus 1 by K3. Or, if there are 5 springs, you can write it as 1 by K equals 1 by K1 plus 1 by K2 plus 1 by K3 plus 1 by K4 plus 1 by K5 and so on. If there are only 3 springs, you can simplify the equation to find the effective K value as K equals K1, K2, K3 divided by K1, K2 plus K2, K3 plus K3, K1. Cyclic order 1, 2, 2, 3, 3, 1. For 2 spring combination, series combination, the same expression reduces to K equals K1, K2 divided by K1 plus K2. Here, the equivalent value of K is smaller than the smallest value of k in the combination. Suppose k1 is 1, k2 is 2, k3 is 15. Then the equivalent k will be less than the least, that is 1. So k will be less than 1. So if you want to reduce k, you can join a number of springs in series. In parallel combination of 3 springs, here it is shown in the figure, k1, k2, k3. These springs have an equivalent k equals k1 plus k2 plus k3, additive law. So if you want to increase the stiffness, of course, provided you have a number of springs, you can connect them in parallel to increase the stiffness, which is common practice in mechanical engineering. So k equals k1 plus k2 plus k3 plus etc. additive law. It obeys additive law, just like resistance in series. Springs in series obeys resistances in parallel. When you consider the form of the formula. Thank you a lot. We will see the rest in the next posting.